Yeah, Assalamualaikum and good morning. So today we start our class on a boundary layer. But before that, I would like to give you a brief introduction between the relationship between what you learned previously in ideal flow chapter with the boundary layer. So I think previously in Fluid Mechanics 1, you already learned about the characteristic of fluid, which is one of them is called no slip condition. So what is no slip condition? So in fluid dynamics, the no slip condition for viscous fluid assume that at a solid boundary, the fluid will have zero velocity relative to the boundary. So the fluid velocity at all fluid solid boundaries is equal to that of the solid boundary. Conceptually, one can think of the outermost molecule of fluid as stuck to the surface past which it flows. Okay, the simple words for no slip condition is the molecule of fluid is stick very hard on boundary, on solid boundary. So mean when it slip very hard, so it cannot move, so it will create zero velocity. So that is the phenomenon of no slip condition. So the idea of no slip condition is already taught in fluid mechanics 1, especially in viscosity chapter. I think you still remember how to solve problems of viscosity. You use the idea of Newton viscosity's law. So and then we will create the velocity distribution. So the velocity distribution occur because there are velocity equal to zero at the surface condition, at the surface area. So the idea as explained here, so the cause no slip condition exists because of viscosity. The no slip condition for viscous fluid assumes that at a solid boundary, the fluid will have zero velocity relative to the boundary. So and then, so what is the difference in this chapter with the previous in ideal flow? So in ideal flow, we assume that the no slip condition is not occur. So means that the molecule that is moved on the solid surface is not stick on the surface. So mean there are no zero velocity for all the molecule in that flow. So this is the major difference between ideal flow that you learned previously with the boundary layer that we will learn in this chapter. So another thing that you should know is the difference between the idea of ideal fluid and the real fluid. So the ideal fluid means what you learn in ideal flow. So the ideal fluid have no shear stress and also have no viscosity. So the word of no shear stress and no viscosity means that the effect of shear stress and the effect of viscosity is not appear in ideal fluid. That's why in ideal flow, so you found that the streamline is very smooth when it flow around aerofoil or when it flow around circular shape. So because there are no effect of shear stress and viscosity, so you will find that there is no resistance between fluid molecule and solid surface. So what do you mean by the meaning of no resistance means that the fluid, the molecule will not stick on the surface. So you know the reason why molecules stop on the solid surface, because there are a lot of resistance. So because there is no resistance, so means that the molecule will flow on the solid surface. So means that it is a slip condition. So means that the molecule will slip on the solid surface. So according to these three ideas, so we found that in ideal fluid, so that you learned previously in ideal flow, there are no boundary layer. Okay, but in this chapter, so we will learn about real fluid. So real fluid means that for sure, it will show the effect of shear stress, and it also shows the effect of viscosity. So because the fluid has viscosity, so means that the fluid molecule will give resistance to the flow. So when it give molecule, when it give resistance to the flow, so means the no slip condition is actually occur. So according to this, so the one phenomenon that is very important to be researched called boundary layer was occur. Okay, I will show you a video about this. Okay, I stop sharing first. Okay, can you see my video? Can you see a video there?
Yes, Teacher.
Okay. So if you see this video, okay, so this is actually a tube. So inside this tube, we put an ink. So and then the water flows from right to left. So you could see here that if we let the ink flows out, so and then it is clearly shows that the fluid is moving from right to left, and you will find that the ink over here is clearly flows to the left, but the ink, if you see here, okay, there is ink that stick very hard on the surface here. Even when the flow keep continue, so you will find that this ink is remain on the solid surface here. So it is occur because there is no slip condition occur for among these molecule on the solid surface. So this is the evidence of no slip condition. So another example for no slip condition is you will find that there are lumot or something like that, okay, that stick on the surface of pipe. So and I will show. Okay, I will show you another videos. Okay, I will show you about boundary layer. Okay, why we need to learn about boundary layer. Okay, so this is actually the experimental to show that it is the velocity distribution actually different when no slip condition occur. So this rectangular area of white is actually the we have a special idea to show the visualization of molecule. So we put an ink actually here. So a special ink. So we have a very white area here. So if there is no object, so the rectangular is remain on its shape, on the rectangular shape. Okay, however, when these fluid flow on flat surface like this, so you could find that there is molecule that stick on the surface here. So that's why we could see that the rectangular area here is a little bit distorted. So this occur actually, this is the velocity distribution actually. So what is the meaning of velocity distribution? So we could assume that at this point, the velocity is equal to 0. And then in the mid area here, in the middle area here, we found that the velocity is a little bit slower compared to the molecule at this area, because this molecule, this area, the molecule will travel at its maximum velocity. So we found that at this area, the molecule is actually travel less than the maximum velocity. And then at this area, the molecule is increasing, the velocity is increased towards the maximum velocity, and at some certain point, we found that the molecule will travel at the maximum velocity. So after this, so the molecule will have a constant velocities. So this is the example of the creation of the formation of boundary layer. So the area here, okay, so is actually, we call that the boundary layer. So I will show you another video after this. So you could imagine that this is without any object. So, and then when we put a flat plate here, so you will find that the velocity distribution occur. So means that after this, when we explain about velocity distribution, please believe that actually the velocity distribution is a physical phenomenon. So means that the velocity distribution can be proved in experimental work. Okay, so in next video, I would like to share here is actually to prove that the boundary layer is actually a physical phenomenon. Means that the boundary layer is actually can be proved in experimental work. Okay, so we have a fluid here. So, and then this is the flat plate. So then we move this flat plate from right to the left. So you will find that when we move, you could see that we could see that there is a very thin layer occur on the flat plate. So this is actually the boundary layer. So when the speed is increased, we found that the boundary layer will become smaller and smaller. Okay, you could see here. Okay, this is what we call the velocity distribution. Later on, we will discuss about this. But in this introduction session, so I hope you could understand that we learn about boundary layer, and boundary layer is actually a physical phenomenon. We could prove it in experimental work. Okay, so I stop this video, and then I would like to show you another slide. Okay, so we go for the notes for boundary layer. So we go for the introduction of boundary layer. Okay, what is the importance of why we need to learn about boundary layer? So in ideal flow, so I think at the end of the ideal flow, you calculate about the lift force and the drag force. But the lift force and the drag force that you calculate in ideal flow is actually not reflect the real calculation, because there are no resistance. Okay, so and now we try to calculate again the lift and the drag force, okay, by using the idea of boundary layer, because, okay, the existence of boundary layer is the major contribution of lift and drag. Okay, let's say we have an aerofoil like this. Okay, so we have an aerofoil like this, and I hope you could understand that if we have a free stream velocity, a fluid move from left to right like this, so the fluid will flow on the aerofoil like this, and a part of this flow will flow under the aerofoil like this, so it will create difference of pressure. So this, the difference of pressure will create lift and drag force. Okay, and then to differentiate between lift and drag force, I hope you could understand that force that move on x-axis, so or force that move parallel with the flow of fluid, so it's called the drag force. So you could see here the FD here is parallel with the fluid flow. So the parallel force that occur, the force occur parallel to the fluid flow here is called the drag force. So, and then the force that occur perpendicular to the drag force here is called the lift force. So means that if you have this situation, so normally we will have two types of force. One is drag force and one is lift force. So, and then if we want to interpret the existence of drag force and lift force using the mathematical equation, we could write like this. So means that the drag force is actually the integral of dfx, means the total. You know that when you integral something, you are calculating the total amount of that force. So the integral of the integral of dfx means the drag force is the total force that occur on the x-axis. So, and then for the lift force, we could write in mathematical symbol as integral of dfy, mean it is the summation, the total force that occur on y-axis. So this is the y-axis and this is the x-axis.
Hello, Doctor.
Oh, sorry. Saya mute. Okay. Okay, saya ulang. Okay, saya ulang semula. Okay, so in this chapter, so we will focus on calculation of lift and drag force. Why? Because previously in ideal flow chapter, at the end of the ideal flow, you calculate the lift and the drag force, okay, according to the ideal flow condition. However, in ideal flow condition, the resistance is not take into account, because in ideal flow, there are no resistance. And now in boundary layer condition, in boundary layer chapter, we will use the idea of boundary layer to calculate lift and drag force. So to differentiate what is lift and what is drag force, I hope you could understand this terminology. So for example, we have one object, an aerofoil like this, okay, and then we have a fluid flow from left to right, and we shows at as capital U here. So, and then it will, because it has angle here, so the flow will flow on at the upper part of the aerofoil, and another flow will flow at the bottom of the aerofoil. So it will create different velocity. So the different velocity will create different amount of pressure, and then the higher pressure will push this aerofoil up. That's why we need to have certain angle to fly our aeroplane. So this is the basic idea of aerofoil. So, and then to differentiate between lift force and drag force. So the drag force is actually force that occur parallel to the airflow. So if you found that the force which is parallel with the airflow like this, so you could call it as a drag force. So, and then the lift force here is actually the force that perpendicular to the airflow. So in this diagram, you will find that so the drag force will occur on y-axis, on x-axis, and the lift force will occur on y-axis. So, and then if we want to illustrate, or we want to write this phenomenon into mathematical equation, we could write like this. So the drag force can be written as the integral of dfx. So you know that the integral here is actually to calculate the total amount, the sum of. So the total amount of forces that occur on x-axis. And then the lift force here can be written as integral of dfy, means that the total amount of forces that occur on y-axis. So this is the basic mathematical idea to relate with drag and lift force. So, and then now we try to interpret, or we want to expand this mathematical equation into real equation to be used to calculate drag and the lift force. So what we should do is we try to evaluate that one with one small area like this. So previously we have aerofoil like this one. So, and then we just take a small area here, to be evaluated. So, and that small area can be determined or can be written as dA. So this is a small area from that aerofoil, and then we write as dA. So dA means a small area of that particular object. So, and then we have a fluid flow from left to right, and we mark as capital U. So this symbol is actually not an formal symbol. So this is only to show my handwriting. This is only for my handwriting. I always write U with a bar on it, like this one, to show, to differentiate between capital U and small u. Because in boundary layer chapter, we will use two terms. One is capital U and one is small u. So to make sure that you write a proper terms, so I propose to you to write capital U with U like this and a bar on it. Okay, so when we have this situation, we could say that actually there are two types of forces occur or happen on this situation. So one is, as I said previously, when we have different value of velocity, so it will create different value of pressure. So I think this is a very common idea. We learned about this from the Bernoulli equation. So, and then the relationship between pressure and force can be written like this one. So means that we have velocity here, and then the velocity will create a pressure on this surface, and then pressure that occur at this area will interact with the area here. So, and then the multiple of pressure and area will give us force. So this is the first idea, the first type of force that occur when we have this situation. So, and then the second force is actually occur because of the viscosity. So what is viscosity? As I explained previously, viscosity will create no slip condition. So no slip condition means it create resistance. So means from the resistance that occur on the surface, so it also create force. So this idea is actually learned in Fluid Mechanics 1 in Viscosity chapter. So I think in Viscosity chapter, you already learned about Newton's law of viscosity. And one of the equation that used on that time is F is equal to tau A. So tau here is actually the shear stress from the molecule that acts on the surface. So you know that we have a surface here, for example. So we have a molecule here. So the molecule will stick very hard on the surface. So this is what we call as no slip condition. So in Fluid Mechanics 1, we write U is equal to 0 here. Okay, because the resistance here is very hard, so means that you need a little bit, you need some amount of forces to move this molecule. So the total force need to be used to move all the molecule on the surface can be shown as this equation. So means that the total force here, okay, can be calculated by using the idea is the shear stress tau here multiple with the area of the plate here. Okay, so I hope you could understand the basic idea of tau times A. Okay, so because we have two forces here, one is force that comes from the pressure because we have different of velocity, and another forces is actually comes from the resistance here, the shear stress. So what we need to do is actually we need to total up all the forces that occur on that area. So we start with our free body diagram like this. So for example, we have this TA. So we have a small area here, DA. We have DA. So and then we know that pressure will act on surface perpendicular. So we learn about this in Fluid Mechanics 1, especially in hydrostatic force on plane or curved surface. So we assume that pressure will act perpendicular to the surface. So we could write the force is actually work like this. So it would work 90 degrees to the surface. So from P times A will give us force. And then shear stress is actually works parallel on the surface. So we could write tau A like this. So mean it must work parallel on the surface because shear stress is actually resistance that occur on that surface. So and then after you write this free body diagram, so you could understand that to calculate the total forces, we need to total up them according to their axis. So means we total up X force that occur on x-axis, and we total up all the forces that occur on y-axis. So to do this, so we distribute the forces according to its axis. So let's say we have PA here. So we could split it into PA cos theta for x-axis and PA sin theta for y-axis. So assume that this is the angle. So and then for tau A here, we could have tau A cos theta for y-axis and tau A sin theta for the x-axis. So and then I think you already know how to do this. So we get back our basic equation for drag and lift force. For drag force, it is a force which is parallel to the airflow. So yeah, we write down as dfx, and then we put all the forces that occur on x-axis. So we have P cos theta dA. dA here is the area, and the tau is tau sin theta dA. So and then for lift force here, so this is the integral of dfy, mean all the forces that occur on y-axis. So we have P sin theta dA and tau cos theta dA. So means that if we could fulfill all the parameter inside these two equations, so we could calculate the value of drag force and the value of the lift force. So this is the basic idea about lift and drag force that occur from the inclined plate. Okay, so let we analyze this equation. So from this equation, we found that the pressure here can be measured. So I think you already know how to measure pressure using U-tube manometer. I think in fluid mechanic 1, we learned about how to do the pitot tube, pitot static tube, and so on and so forth. So means that if we have an inclined plate like this one, and then you create a hole here, and then you connect with a U-tube manometer here. So when the airflow move on the plate, so it will give you the difference of mercury here, the difference of manometer fluid. So the difference of this manometer fluid will give us the amount or the value of the pressure. So means that the pressure can be measured. So sin theta, it depends on the angle of this plate. So means that we could calculate the value of sin theta. And dA here is actually the real area of this plate. So means that the value of dA also can be calculated. So and then the dA here is also can be calculated, and the cos theta is also can be calculated. So the problem is how to calculate the value of shear stress. So the problem here is we cannot directly measure the value of shear stress. Why? Because the shear stress is actually depends on how strong these molecules stick on this surface. So means that because it is very micro world, and it is very difficult to measure this value of shear stress. So means the value of tau here is remain it's remain difficult to get the value. So means that we cannot solve the drag force here because we don't know the value of shear stress. So, but okay, by using the idea of boundary layer, we manage to calculate the value of shear stress. That's why we need to learn about the boundary layer, because the understanding of boundary layer will help us to determine the value of shear stress. So means that after we get the value of shear stress from the idea of boundary layer, then we could calculate the value of lift force and also the value of drag force. So and then, so from the experimental works, Okay, so for from the experimental works, and then from the dimensional analysis, I think you already learned about dimensional analysis in fluid mechanics 1. So we actually can estimate the lift force and the drag force from the experimental work. So I'm not going to to teach about the dimensional analysis and so on and so forth. So but the basic equation that you need to understand is from the experimental work, we could calculate the drag force and the lift force by using this equation. So we have FD, the drag force, times CD, the coefficient of drag force, 1 over 2 half rho A and U square. So the rho here is the density of the fluid. The A here is the area of the object, and the U square here is the velocity of moving fluid. Okay, so this is the basic equation that we get from the experimental. So I think you could you could understand that from the experimental, from the dimensional analysis, actually we could get the value is actually FD equal 1 over 2 rho AU square. And then when we compare with the experimental, we found that we need to add one coefficient here to normalize or to make sure that our calculation and the experimental work will give the same amount. So the work here, CD here, is actually the coefficient. So I think in fluid mechanics 1, you could imagine that, for example, we have a tank like this. So, and then when the water flow here, so we have a coefficient of here is CD. So, but the word D here is actually the coefficient of discharge. Okay, because when in real situation, the velocity that comes out from this hole is actually a little bit slower compared to the theoretical calculation. Okay, same goes to this idea. So we need to put the coefficient here to normalize or to make sure that our calculation is same with the experimental works. So please remember this equation. Okay, please remember this equation because we will use this equation in the calculation later. So however...
Professor, I have a question. Can I ask a question?
Okay.
Okay, for the area inside the drag force
Yes.
equation, is it for the surface or the thickness?
For the surface. Because
Okay, thank you.
for example, we have a plate here. Okay, so the surface here is actually because the fluid flow, the molecule will travel from here to here. So you need to calculate all the area here. Means the length times the width here. Okay, can you get it?
Yes, I got
Okay.
it. Thank you.
Okay, so this is actually the area here is actually the general idea how to calculate the area. However, in certain research or in certain works, you must alert with how to calculate the value of area here. So I write here in Malay. So the value of area here is actually changed according to the definition. Okay, for example, so we have a sphere here. So the sphere is like this, okay? And then according to the experimental, it is okay for us to take the area is the projection area of this sphere. So means projection area, I think you already know. The projection area means the shadow of this sphere. So for example, if you have light here, so you have light from here, and then the shadow of this sphere will give us a circular area. So means that it is okay because the experimental shows that the calculation is still correct when we get the area of the projection area here. So, and then for example, we have a cylinder like this. Okay, for falling sphere, the common value of CD is 0.5. So, and then for example, we have a cylinder like this, and then the cylinder falling down like this one. Okay, so means that the air flow is moving from bottom to the top like this. Okay, so it is okay for us to calculate the area for this situation by having its front area like this. Okay, so and then if we use the same cylinder, but we change the orientation. So for example, we put the cylinder is like this. So the area is not the circular area anymore. So the area is the projection area. So means that the area of the rectangular area here. So and then the value of CD is increased from 0.8 to 1.1. So means that for calculation of area, it's depend on the situation. But normally in common shape, for example, sphere, cylinder, aerofoil, and so on. So it is you could find it in textbook. So for example, in aerofoil like this one. So normally people will calculate the area here. For example, this is the aerofoil. The area here of aerofoil, it is okay for us to take the area of rectangular area. So we just calculate the length of the aerofoil. We multiply with the width of the aerofoil. Okay. It is okay not to calculate the real area on the top of this aerofoil. So it's depend on the situation. Okay, now I would like to focus on drag force first. Okay, so we have lift and drag force. Okay, so we focus on drag force first. Okay, so actually drag force in specific research, we could divide into two types of drag force. One is, we call it as a drag force, and certain textbook call it as form drag form, and so on. And another one is a skin friction. So what is the difference between these terms? So this is actually, the drag here means the resistance according to the surface which is perpendicular to the flow. And the skin friction is actually the friction or the resistance that occur when molecule travel from front to the end of the object. Okay, for example, if we have, okay, I enlarge this picture. Okay, for example, for the flat plate like this, okay, a very thin plate like this one. So we found that at the front end here, so the thickness is very small. So means that the area of the thickness will not give so much resistance. That's why we say that the form drag here is almost equal to 0. Because if you have a very thin plate, so the resistance that occur at the front end of this plate is actually not give you so much trouble. So and then, so the problem is the resistance is actually occur when the fluid travel from here to here. So this is the resistance that occur on the skin. So we call it skin because this is the total area traveled by the molecule. So we have the skin friction, we have the form friction. So and then, for example, the aerofoil like this one. So you know the aerofoil, it has a streamlined shape. So mean shape that could give less resistance. So you will find that the form drag here means the resistance because of its thickness is around 10%, and the resistance that occur on the skin here is 90%. So and then for a cylinder like this one, so the drag force that occur according to the resistance of the front end like this, okay, is very high. It is 90%, but the skin friction is 10%. So and then if you have a thin plate okay, put perpendicular like this one, so it will give you 100% resistance because of the area here. So, and then it will give you 0% its skin friction because the thickness of this plate is very small. So means that we assume that the resistance from the skin is minimum. So I hope you could understand the idea of boundary layer right now. Okay, the introduction of lift and the drag force. So, but however, in this chapter, we are focusing on calculation of this area because this thin plate is actually will give us 0% drag force in terms of surface, and it will give us 100% resistance from its skin friction. So we will focus on this first before we could calculate another situation. Okay, sampai sini boleh ke? Any question? Ada soalan ke?
Doctor, can you repeat what are the effects of the drag force on the object using
Here,
the streamline?
using the streamline. So the idea is, okay, so in drag force, we have two type of drag force. Okay, one is drag force occur because you have area which is perpendicular to the airflow. So for example, if you have a plate and then the orientation of plate is like this, so means that the area which is perpendicular to the streamline is very huge. So it will give you 100% drag force or foam drag here, and it will give you 0% skin friction. However, if the same thin plate like this, okay, you put like this one horizontally, so you will find that because the thickness of this plate is very small, so means that the area which is perpendicular to the airflow is very small. So it will give you 0% foam drag, but it will give you 100% skin friction. So what is skin friction? So skin friction is the resistance that occur from the front end here, from the starting point here until the end of this plate. So means that the molecule will travel from here until here. So along this area, along this distance, so the fluid will give you resistance. That's why the skin friction is 100% for this situation. But because it is very thin, so the foam drag is 0%. So but in our syllabus, so we will focus on this situation first. Because our aim is actually to calculate the value of shear stress. Okay, please remember that as I said here, so according to this equation, the only unknown parameter is actually the value of shear stress. And shear stress is occur because of the no slip condition that occur on the surface of this object. That's why in this syllabus, in this topic, we are focusing for this situation.